calculate the derivative of each of the following functions, f of x. Please note that while the same variable and function name is used for each, none of these functions should be considered as related. Do not expand and simplify after using the quotient, product, or chain rules. Please do not misunderstand that last sentence as an instruction not to simplify at all. What I mean specifically is, like, don't, FOIL out the products that will be in the sum after using the chain rule, right? When you're, not the chain rule, I'm sorry, the product rule. When you're using the product rule, right, you will have at the end a sum of a bunch of products. Do not expand those products. But, like, if you've got 4 over 2, that's 2. Don't leave it as 4 over 2. There's just practice. You'll see. Sometimes, it becomes simpler to do calculations when you leave or when you actually calculate out that arithmetic, right? But sometimes there's no need to expand after using the product rule. I just want to know that you know how to use, say, the product rule, or the quotient rule, or the chain rule. But specifically for the chain rule, parentheses are important, right? Because we need to be able to tell what order products, and specifically products over certain sums, are being operated in. Anyway, those were the instructions that I just read aloud a little bit ago. I'm going to zoom in now so we can see the problems a bit more clearly. 1. Take this derivative. I'll do it in this color. F prime of x equals, I'll do it on the next line. So again, we use the power rule here. 3 times 4 is 12. 4 minus 1 is 3. Okay? 12x cubed minus 5x to the 4th plus 2 minus 2e to the x. All right? So that last one, 2e to the x, the way that was done was just using the constant multiple rule, right? Minus 2 times e to the x. The derivative of that will just be minus 2 times the derivative of e to the x. But the derivative of e to the x is just itself. Okay? So this was number 1. Alright, so for number 2, it looks like we're going to need the quotient rule. Alright, low d high minus high d low over low low. I'll write that in the corner here. You can't see that high up, sorry. There you go. Alright, and or maybe I'll put a capital D, just so it's really clear that we're taking a derivative here. I'll even do it in a different color. We'll get really color-coded here, folks. Alright, forget it. Anyway, for number 2, it'll be 2x cubed minus 4x times the derivative of 3x squared minus ln x. That's a difference, so we can just Take the derivative of it piece by piece. That'll be 6x minus 1 over x. I'm sorry that my x's keep coming out looking like alphas. I'm barely picking the pen up, I guess. And it just keeps coming out looking like that. Oh no, I don't want that. Go away. Sorry. Alright, so this was low d high minus high d low. That's ln x there. D low will just be, again, 6x squared. Not again. Sorry. Minus 4. All over 2x cubed minus 4x quantity squared. I'm sorry. My handwriting is atrocious. Oh, good grief. There we go. All right, number 3, arctangent is one of the 5 trig derivatives I would say are worth memorizing. All right, the 5 that I would say are worth memorizing, I'll go back. That was the derivative for number 2. Anyway, number 3, arctangent is one of the 5 trig derivatives I would say are worth memorizing. The other 4 being sine, cosine, tangent, as well as arcsine and arctangent. All of these can be found in Chapter 3 of your textbook, so you should look up their derivatives. All right? Anyway, the derivative of arctangent, which is the inverse function of tangent, and technically could be derived through implicit differentiation, in fact, let's do that right now. Right? If y is equal to arctan, what that means is that the tangent of y is equal to x. And specifically that we're looking at a y in the principal domain of the tangent function. Principal domain of tangent is in fact the same as the principal domain of sine. It is that y is between these two angles. Negative pi over 2 and pi over 2. All right? Over that entire interval, tangent hits every possible value it could attain, and it does so exactly once, thereby becoming an invertible function. All right? Anyway, here, the derivative then we would take through implicit differentiation. The derivative of tangent is secant squared. Whoops, sorry. But we would have to multiply that by y prime. And the derivative of x is just 1. All right? Solving for dy dx, then, we get that y prime is 1 over secant squared y. But secant is the reciprocal of cosine, so 1 over secant squared is literally just cosine squared y. And we would prefer, of course, to express that in terms of, well, actually, you know what? It might make most sense to just leave it as 1 over secant squared. We'll see. Anyway, we'd like to express this in terms of x, not y, right? And the way that we would do that is by using the fact that the tangent of y is equal to x. So we can set up this little triangle here. Tangent, remember, is opposite over adjacent, right? And so if the two legs of the triangle are 1 and x squared, that would mean that the hypotenuse is the square root of 1 plus x squared, because 1 squared is just 1, right? But then, what does that mean? That the secant of y is, well, remember that the secant, that's the reciprocal of cosine, so secant is 1 over cos, and cosine is typically adjacent over hypotenuse, so that means that secant is hypotenuse over adjacent, and so dy dx is the reciprocal of secant squared. Well, hypotenuse over adjacent, well, that's just square root of 1 plus x squared. We square this and take, sorry, it's not fitting on the edge of the screen. This is what you get for using weird Windows brand products. Oh, good grief. It's supposed to be a 2 there, folks. One plus x squared. Anyway, we square this and take its reciprocal, as is suggested here, right? We've got secant, it's this value, but we want 1 over secant squared, so this just turns out to be 1 over 1 plus x squared, right? That's why the derivative of arctangent is 1 over 1 plus x squared. Again, just summarizing everything here. d dx of arctan is 1 over 1 plus x squared, which is something that you can figure out with implicit differentiation and just some know-how about triangles. Okay? Number 4, you would use the chain rule and the product rule. The way that I see this is that first and foremost, it's a square root of another function. It is in fact a square root of a product. I did, however, see a student who rewrote this immediately as x to the 1/2 times sine to the 1/2 x, right? And then they just use the product rule, and on each of the factors, they use the chain rule. That's an interesting way to do it for sure. I will show you how to do it this way. All right, so this is a product, first and foremost, of x squared with not x squared, square root x with square root sine x, right? But in each case, we can take the derivative using the power rule, all right? So the product rule says that we take the derivative of 1, leave the other alone, and then we add that to basically doing it with those roles flipped, right? So 1/2 x to the negative 1/2 sine 1/2 x. All right, that's easy enough. But in the next factor, notice that we need to use the chain rule because we're taking the square root of not just x, but of another function, of sine x. So we will still have 1/2. I'm just writing the coefficient out front. Now I'm leaving the x to the 1/2 alone. And it'll still be sine to the negative 1/2 x. Sorry, I couldn't fit this all on one line. Yeah, I don't know what to say. Can I select this? Maybe? No, these are drawing boxes. Oh, interesting. All right, anyway. Right here. Nope. Yeah. Right there should go a times the derivative of sine, right? Because the chain rule says that we take the derivative of the outer function. The outer function here is the square root, so that would be 1/2 the argument to the negative 1/2, and we've got that 1/2 sine to the negative 1/2. But now we need to multiply it by the derivative of the argument. And in this case, rather, that is cosine. In fact, I think I might be able to fit it. No, I cannot. I can, kind of. I'm sorry that is terrible looking. I'm just going to put the whole second summed down here. All right. So that is the answer to number 4. Number 5 is a product rule kind of thing. Don't simplify after doing this one. I'm going to rotate this real quick. Oh, rotate. Alrighty. We only need that much. Alright, so that is the derivative, the original function that I want to take the derivative of. We can just barely see the f of x, right? We don't actually need that in there. And now I can take the derivative here. I've got all the space I need, right, to do a product rule. I'm gonna do it line by line because remember, since this is an a, b, c that we're taking the derivative of, it's going to be a prime b c plus a b prime c plus a, b, c prime. And each of these capital letters here are, binomials like 2x squared plus 3x or x cubed plus 4x. So all of these derivatives are going to be kind of lengthy. So I'm going to write each of these on their own line. Okay? So the first derivative, and I know there are some folks, I don't know why. Some folks take the derivative going from the right to the left. Some folks go from the left to the right. So long as you take the derivative of each of the factors and add all of these things up, it doesn't really matter what order you do it in. For instance, I could start with the middle factor. I could leave 2x squared, Jeez Louise. Really cuts away from my point when my marker is slowing me down. I could leave the 2x squared plus 3x alone and then multiply it by the derivative of the middle term, which would be 3x squared plus 4 times, and then just the x fourth plus 3. Again, left alone. Plus, so I've taken the derivative of the middle term. Now let's leave the first two alone and do the last. Again, the order is totally arbitrary. It doesn't actually matter, so long as you do it to each of the factors. 2x squared plus 3x plus, or times rather, x cubed plus 4x. Now the derivative of x to the fourth plus 3 is just times 4x cubed plus, and now we take the derivative of the first one. That would be 4x plus 3 times x cubed plus 4x, times x to the fourth plus 3. And don't expand and simplify this, but notice that, right, I didn't write 2 times 2. I wrote 4. Or, yeah, that's really the only case. There would be unresolved arithmetic, I guess, in this particular case. Anyway, I'll be right with you. I will begin this question, which is number 6, the same way that I did when I was mentioning it in class, is that on this graph, this x that's going through the origin. Sorry, my screen just, I didn't want to let it go away. Anyway, this x going through the origin is not actually part of the graph, and you can test that real quick. Right, this line is y equals x. If y and x were the same thing, then their square would be the same thing, and this difference would equal 0, not 1. And just, pick out the origin, 0, 0, plug them in, x and y equals 0, you'd get 0, not 1. Alright, the graph is just this kind of, these sideways kind of bent shapes. Both of them. Both of them are part of the graph. But notice that there are no x-coordinates strictly between -2 and +2, but that the tangent lines at that point, that is at, let me draw it, at -2, 0, that tangent line is a vertical line. Sorry. So, the derivative won't be defined there because vertical lines have an undefined slope. Right? There is no change in y over change in x, or change in x over change in y. Right? It doesn't change x. Change in y over change in x doesn't change. Good grief. So, what's the derivative? first thing I'm going to do is I'm going to rewrite this as 1/4 x squared minus 1/4 y squared. There's no particular reason why we should or should not write it this way. I just think that it's a little more familiar to write these variable terms with coefficients. Right? And dividing x squared by 4 is the same thing as multiplying it by 1/4. So why not just write the coefficient of 1/4 out front, where coefficients belong? Right? So we take the derivative of this using the power rule, multiply 1/4 by 2, we get 1/2 x, subtracting 1 from the exponent 2, which is left with x. And we'd get the same thing for 1/4 y squared, only we have to remember that at the end we multiply by y prime, which in this case I will write as dy dx. All right, and the derivative of 1 is 0. Now we add, add 1/2 y dy dx to both sides. And then multiply what remains by 2 on each side, right? And this way the 1/2 and the 2 will cancel. These will have canceled already. And we'll get that x equals y dy dx. And so finally, dy dx, or y prime, which is what we've been looking for all this time, is just x divided by y. Okay. And now notice that that thing that I couldn't seem to get my words around earlier, about how at -2, 0 and 2, 0, the tangent lines were vertical and so had an undefined slope. Slope, remember, being change in y over change in x, would be undefined for a vertical line because there is no change in x. That would be 0, right? And we had precisely that at the tangent lines at these kind of cusps, or I believe they're probably called vertices. Oof. That is not how they meet. Sorry. Anyway, at these two tangent lines, at the point -2, 0 and the point 2, 0, which this is not a great drawing on this side, but 2, 0, I mean, just look at this picture. Look at this picture. This picture is much better. But, you know, the tangent lines are supposed to be vertical. Their slope is undefined. And it makes sense because at those 2 points, what are the y coordinates? 0. And that is precisely where this derivative is undefined, where y equals 0. Let's move on. You're not going to see a question like this on your test. I have already done an example in class of the kind of question you'll see. You'll be given a point and asked to produce its tangent line, but I said I would post answers to this, so I will answer this. List the 2 points on the graph where the tangent line will be parallel to the line square root of 5x. Do your work below. So parallel means it has the same slope. So we're looking for a place where dy dx, that is, x over y, equals the square root of 5. But if this is true, right, if x over y equals the square root of 5, then x equals the square root of 5, y. And notice that the y here is not under the radical. So perhaps it would be a better idea to write it as y square root 5. Okay? But the more important thing is that being on this graph means it still has to satisfy this equation, right? So we can plug this value in for x, right? So rather than x squared over 4, we'd have y root 5 squared, and that would just be 5y squared over 4 minus y squared over 4 equals 1. But this arithmetic on the left just becomes 5y squared minus y squared. That's 4y squared over 4, or just y squared, equals 1. And so y is plus or minus 1. All right? And if we want to know now what x is, we would just go back to this equation. So if x divided by y is the square root of 5 and y is positive 1 or minus 1, that would mean that x is plus or minus square root 5. Where again, the signs of x and y would have to match, right? Because their quotient is positive. And a positive divided by a positive is positive. A negative divided by a negative is positive. But if x and y's signs do not match, then you wouldn't get positive square root 5. You'd get negative square root 5. Right? So the answer here, of course, looking... Sorry, I didn't mean to scribble all that. Looking at the way that it expects you to enter your answer as a couple of ordered pairs. And in fact, it asks you to write them in a certain order. It wants you to give the first ordered pair as the one where the x-coordinate is negative, right? So where x is minus square root 5. But if x is minus square root 5, then y would have to be negative 1, because, again, I will recall that x divided by y is equal to square root 5, a positive number. So their signs have to match. All right, and then the one with the positive x-coordinate would just be square root 5 over 1. And this, in the box here, is your answer to part B of whatever number this is. 6. This is 6 part B in the box here. Okay? Wonderful. Moving on. Number 7. Calculate the derivative using logarithmic differentiation. I'm going to turn this sideways again. I'm going to send this to the background. Or not the background, but at least move it behind. There we go. Alright, so that's what we're taking the derivative of with logarithmic differentiation. Perhaps I can zoom in a bit. All right, wonderful. So the steps of logarithmic, again, have us beginning by taking the ln of both sides. So that would be ln y. Oh, sorry. Ln y equals the natural logarithm of this stuff on the left. All right, this stuff on the left here. I'm not going to rewrite that right now, but we can simplify this. The natural log ln of this whole quotient, well, that's the natural logarithm. Natural logarithm of a quotient of a division is the difference of logarithms. So I can write it as the logarithm of the numerator minus the logarithm of the denominator. So this would be ln x plus 2 to the 6th times x cubed minus 4x minus the natural logarithm of 2x minus 3 quantity cubed. All right. Next, I can split this logarithm of a product up as a sum of logs. And now, in this case and in this one, where I have exponents, oh, I'm sorry. I didn't realize that that had been cut off. My bad. Anyway, in those two instances where I now have exponents, I can bring those out front. And I get 6 ln x plus 2 plus ln x cubed minus 4x minus 3 ln 2x, not plus, sorry, 2x minus 3. And this is all still equal to ln y. All right? And this now is what I take the derivative of using logarithmic. Or not logarithmic. Well, kind of. This is logarithmic differentiation. But the derivative of the natural logarithm of a function is just the derivative of that function divided by the given function. So in each case, this ln of x plus 2 or ln of x cubed minus 4x, the derivative of that whole expression will be the derivative of the x plus 2, for instance, divided by x plus 2. The derivative of x plus 2 is just 1, though, times 6, don't forget that. Divided by x plus 2, we'll have 6 over x plus 2. In the next case, the derivative of ln x cubed minus 4x, well, that's just 3x squared minus 4. That's the derivative of x cubed minus 4x over x cubed, minus 4x. Finally, the derivative of 2x minus 3 is just 2, but I'm going to multiply that by the negative 3. We get minus 6 over just 2x minus 3. And this is all equal to the derivative of ln y, which is just y prime over y. All right, we multiply both sides by y, and we get our expression for y prime, or dy dx. All right. We don't actually write y, though. We write what y was equal to, which was x plus 2 to the 6th times x cubed minus 4x. Sorry. All over 2x minus 3 quantity cubed. And this is what y prime, or dy dx, is equal to. Alright, sorry that I couldn't fit that all on one screen. There it is. Okay. All right. The Next problem is another logarithmic differentiation, except the difference here is that it's not going to be done exactly the same way. When we're simplifying the right-hand side using the log laws, we're going to get a term, a whole polynomial, kind of pulled out as an exponent. It's going to get pulled out front as a coefficient, as a term that we are multiplying the logarithm by. All right? Just like any other exponent would. It's just that here, the exponent happens to be a polynomial. All right? So let's work on that. All right. So again, we begin by taking the logarithm of both sides. We get ln y is equal to ln of x to the 2x cubed plus 4x minus 3. Right? And this whole term here is in the exponent. So using our log laws, when we pull that out front, we are scaling ln x by this whole polynomial. So the derivative of ln y here is in fact a derivative that we need to obtain by using the product rule, because we have one function times another. The derivative of that first function, well, is just 6x squared plus 4, and the minus 3 goes away. And we leave ln x totally alone. And now we leave the polynomial alone, 2x cubed plus 4x minus 3, and we take the derivative of ln x, which is just 1 over x. And this is all equal to the derivative of ln y, which, as always, is just y prime over y. We multiply both sides by y, and we get that y prime is equal to, well, y, recall, is x to the 2x cubed plus 4x minus 3 times this business. So, as small as I can. Shucks. 6x squared plus 4 ln x plus 2x cubed plus 4x minus 3 times 1 over x. This is a times, not a minus. So I guess I don't really have to write anything at all. I can just write 1 over x. And that's sort of just, you know, that's what it means. Anyway, that's our derivative. We do have a plus sign. Right, yeah. All right. All right. Moving on. Ooh, a related rates problem. All right. A spherical snowball melts so that its surface area decreases, all right? So its rate of change, by the way, is going to be a negative value, all right? That means its derivative will be a negative number. If a spherical snowball melts so that its surface area decreases at a rate of 1 centimeter cubed per minute, find the rate at which the radius decreases when the radius is 5 centimeters. The surface area of a sphere is given by 4 pi r squared. 4 pi r squared. And we want to know what the rate of change of... Find the rate at which the radius decreases when the radius is 5 centimeters, all right? And we are being told that its surface area is changing at a rate of 1 centimeters. Oh, I'm sorry, that says 1 centimeter squared per minute. My bad. Yeah, surface area would be centimeters squared, right? Because it's surface area. It's a two-dimensional measurement. So surface area is decreasing at a rate of 1 centimeter squared per second. Decreases at a rate. So what we've got here is that dA dt is equal to -1. All right? And we are being asked for dr dt when the radius is 5 centimeters. All right? And yeah, all the units match. Centimeters squared, centimeters, great. All right. So let's begin by finding the derivative. The derivative here would be dA dt equals 4 pi is a constant, so we really only have to find the derivative of r squared. That would be 2r dr dt, so times 4 pi. That would be 8 pi r dr dt. And now we plug in all of the information that we know, and we find the information we want. So -1 equals 8 pi times r. R is 5, so that would be 40 pi dr dt. And so the rate of change, dr dt, is -1 over 40 pi. And this would be dr dt, so that would be centimeters per minute. Yeah. And it's a negative number, so that just goes to show that it is decreasing. All right. I wanted to just let you know that had you done these calculations with a +1 instead of a -1, you would have just gotten +1 over 40 pi, right? And again, the question is specifically asking, find the rate at which the radius decreases. So if you just ignored the sign altogether, you would have gotten an acceptable answer. It just would have had an opposite sign. All right, but because everything is decreasing, that's why I have all of these negatives floating around. All right, so that's how you would do number 9. Number 10 is a little different. So just give me a minute. All right, 2 pixels travel away from the same point on a screen. So they're starting, say, one's heading up at 3 centimeters per second. And the other one is headed right at 4 centimeters per second. Consider the right triangle formed by their common starting position and the position of the 2 pixels at time t measured in seconds. At what rate is the area of this triangle? So area of a triangle is 1/2 base times height. At what rate is the area of this triangle increasing 4 seconds after the 2 pixels began moving? So the area is 1/2 base times height. Taking the derivative of this, we get dA dt is 1/2 dB dt times h plus 1/2 b times dH dt, right? And we know that dB dt base is 4 seconds, 4 centimeters per second. So this is 4 times 1/2, right? Times h plus 1/2 times b times dH dt, we know, is 3 centimeters per second. And we're looking for dA dt, right? So what we need now is to figure out what h and b are at 4 seconds, right? But we know exactly how to find that because we have their speeds. So base, the speed of the base is 4 centimeters per second. So after 4 seconds, that means it has moved 4 times 4, or 16 centimeters, right? So that is what would go in for base. So we have 1/2 times 16 times 3 plus 1/2 times 4 times height. Well, 3 times 4, 4 seconds at 3 feet, or centimeters rather, per second would be 12 centimeters, right? And now we just need to calculate this, and this will be precisely what dA dt is equal to. So that would be 1/2 times 4 times 12 is 24. Plus rather 1/2 times 16 times 3, which is also 24. It is 48. All right. And that is what are the units. So this is dA dt, where we are measuring lengths in centimeters. So this would be centimeters squared per second. Okay. I want to take a little bit of time to look at, sorry. I want to take a little bit of time to look at these problems, where we're trying to graph certain curves that have prescribed properties. All right, so if you were in my 3 o'clock class, you've already seen number 4 done. And if you're in either of my classes, you've seen the last 2 on the handout from last Friday worked in class. I'm not going to work those again right now. All right, but I do want to go through each of these. Okay? So if you just give me a moment, I'm going to align the screen so that I'm kind of vertical, or what is it called, portrait rather than landscape on my whiteboard. All right, sketch a function that satisfies all of the given conditions. Number 1, we want something that is so increasing, remember, means that the first derivative is positive. Decreasing means that the first derivative is negative. And the second derivative has to do with concavity. It's concave up when the second derivative is positive, and it's concave down when the second derivative is negative. All right? So it's increasing on the left-hand side of -2, but it is decreasing on the right-hand side of -2. And it doesn't seem to be doing... Oh, because it has a vertical asymptote at x equals 0. I see. So, this is number 1 that we're doing. So it has some kind of vertical asymptote at the y-axis, right? And on one side of -2, which I'll mark, -2 is right here. On one side of it, it is increasing, but on the other side, it is decreasing. All right, and it's in fact decreasing on both sides of 0, but it's not defined at 0, so we have to just distinguish that. All right, so it is concave down if x is less than 0, so it's concave down here and here, and it's concave up if x is greater than 0. Okay, all right, I can draw something like this. So it's increasing and concave down. I guess something like this. Maybe not quite so asymptotic. And then it starts decreasing, and then has some kind of asymptotic behavior there, I guess. So maybe with an asymptote at 0, it would look like this, where that peak is at -2. All right, and it goes down forever on this side of 0. And I don't know what it does over here. It doesn't really matter. It can go down towards -infinity, or... yeah, it can't really, because it's decreasing forever this way. I mean, it says increasing, but if we're going to the left, right, it would be decreasing then. Since it's going down forever as we go to the far left, but is also concave down, it can't really approach an asymptote, a horizontal asymptote. Okay? So it would have to just go down towards -infinity. But maybe not so abruptly. Something like that. All right, and then it's decreasing on this side of 0, but it's concave up, so maybe something like that. Okay, and this would be a perfectly acceptable answer to number 1. All right, where again, it changed its increasing, decreasing behavior at x equals -2. All right, and it had an asymptote on the y-axis. Number 2, we want the derivative to be 0 at 0, 2, and 4, and we want it to be increasing over those intervals, concave up, on intervals determined by, it looks like, 1 and 3. So this shouldn't be so hard. And it doesn't say anything about it being even or odd. We can just assume that its behavior on the left-hand side of the y-axis doesn't really matter, I guess. I mean, it does say, you know, things like less than 0, so that does include the left side of the y-axis. Anyway, so it has local extrema, or something going on, with like a flat horizontal tangent line at 0, 2, and 4. All right, and concavity changes, or increasing, decreasing changes from 0 to 1. 1 to 2, 2 to 3, 3 to 4, and then 4 to infinity. So in -infinity, to 0, to 1, to 2, to 3, to 4, to infinity. All right. So from negative infinity to 0, it is increasing and concave down. From 0 to 1, it is decreasing. From 0 to 2, in fact, decreasing. But from 0 to 1, it is still concave down. All right? From 1 to 2, and indeed from 2 to 3, it is concave up. But on this side of 2, it is increasing. And it stays increasing until it gets to 4. But on this side of 3, it is concave down again. And then on the other side of 4, it's decreasing, but still concave down. All right. And we don't have anything about like coordinates, so the height doesn't actually really matter. But let's just see where the picture takes us. Okay. So increasing and concave down looks like this. Then suddenly decreasing, still concave down until we get to 1, in which case it's decreasing and concave up. And then when we hit 2, it starts to increase. And then when we get to 4, it's still increasing, but now it's concave down. And then, when we get to 3, it's still increasing, but now it's concave down. And then when we get to 4, it's still concave down. But now it starts decreasing forever. And so it looks something like that. And this would be an answer for trois, 2. Trois is not 2. I think deux is 2. Trois is what, 4? I don't speak French, I'm sorry. No. Trois might be 3. I'm not sure. I'm sorry to everybody who speaks French. I apologize for my ignorance of French. Let's work on the next one, number 3. So this one tells us some information about asymptotes. All right, so in number 3, in each case, I think what I would recommend doing is like, something happened. What I would recommend doing is marking all of like the points on the graph. Here we don't necessarily have any function values explicitly given, but we do have asymptotes, horizontal asymptotes. As x goes to positive infinity, it's approaching a height of 3. As x goes towards negative infinity, it is also approaching a height of 3. All right? The derivative at 5 is 0. All right? What else is going on? It is increasing on the right hand side of 5. And on the right hand side of 5, it seems to be decreasing. And then it gives us a whole mess of information about the concavity. So we seem to have inflection points at 2, and again, and at 8. So I think maybe I drew a little bit too much of this graph on that side of the origin. 1, 2, 3, 4, 5. Jeez Louise. All right. So, where was I with the increasing, decreasing business again? Right. On this side of 5, it was increasing. On this side of 5, it's decreasing. The concavity changes at 2 and 8, it looks like, between 2 and 8. So 2 would be, hello. So let's fix these intervals a little bit. Alright, so it'll be increasing here, decreasing here. Between 2 and 8, it is concave up. But less than 2 or more than 8, it is concave down. Right? And we have that the second derivative at 2 and 8 are 0. And what was more, I had it previously marked in my last picture, but I don't have it marked here, is that we have some kind of asymptote, a horizontal asymptote at height 3, as we're going towards plus or minus infinity. All right? So let's see what we can get. So it's concave down and decreasing up until we get to 2. When we get to 2, it's still decreasing, but now it's concave up. At 5, its derivative equals 0, and in fact it changes from decreasing to increasing, still concave up. But at 8, it changes to concave down, and it stays increasing forever. And it has this weird sort of horizontal asymptote at 3. Okay? And it is just getting really, really close to this horizontal line at height 3 as we approach negative or positive infinity. But in either case, it never hits this horizontal line. It just gets really, really close to that horizontal line. And maybe my picture over here could be a little bit better to express that fact, but I think I did a pretty good job of it over here. It sort of looks like an upside-down bell curve. Okay? This would be an answer for 3. If you're in my 3 o'clock class, you've seen an answer for the next one, but let's take a look at the next one. All right. So the derivative is positive for x greater than 0, and the second derivative is positive for x less than 2, but it's negative for x greater than 2. And we're told that we have an inflection point at 2, 5. So we are indeed being given a specific point on the graph, 2, 5. Right? We're being told that that is on the graph. All right? And it is increasing everywhere. But on the left-hand side of 2, it is concave up and increasing. On the other side of 2, it is concave down and increasing. All right. It has also 2 asymptotes, 2 horizontal asymptotes. As x goes towards negative infinity, it looks to be approaching a height of 0. Whereas as x approaches positive infinity, this was height 5, 6, 7, 8, it seems to be approaching a height of 8. Okay? And it's increasing all throughout, but it changes concavity at 2, specifically at 2, 5. All right? So that is going to be a place indeed where it has a vertical tangent line. Notice how it has this condition here that the derivative is positive everywhere but 2. It's probably because the derivative is undefined at 2, which means either it has a sharp point or a vertical tangent line. Makes more sense to have a vertical tangent line here. So it's increasing up until that point, again keeping in mind that it has to decrease as we go from left to right down to this x-axis, right? And it's concave up, so it looks something like this. And then at 2, 5, it changes concavity to concave down, but it's still increasing up to the height of 8. And this is what the graph looks like. This kind of swoosh here in black. And this is an answer to number 4. All right, and these 4 exercises, as well as those that we saw in that test that I had been doing for the, however long preceding, these are good practice problems for your exam. Okay, good luck, and hope you're studying hard. Take care.